Welcome back to the deep dive. Today we are jumping straight into something that really challenges a core belief about a major AI architecture.
We're talking about mixture of experts, or MoE models.
Exactly. And the whole idea has always been specialization. This clean divide and conquer approach where a math problem goes to the math experts. Simple.
Well, it turns out it's not so simple. The paper we're looking at is called The Illusion of Specialization, and that title says it all.
An illusion. Okay, so what did they find instead? What's behind the curtain?
They use this framework, committee audit, to trace how data actually moves through the model, and they found what they call a domain-invariant standing committee.
A standing committee. It sounds official. What is that in AI terms?
Think of it as a small, stable group of experts, maybe just 2 to 5 of them, that act as a hidden generalist core.
A generalist course. So no matter the topic, finance, biology, whatever, the same small group is handling the work.
That's what the data shows. This tiny coalition just absorbs most of the computational load, regardless of the domain.
Okay, let's talk numbers then, because this sounds, well, it sounds inefficient if you're building a huge specialized system. How centralized is this across models like Olmo or DeepSeek?
The numbers are, frankly, extreme. They use Jacquard's similarity to measure the overlap of the top experts across different domains.
And what did that show?
The average overlap was consistently around 0.87.
Wait, 0.87. So 87% of the time, the system is using the same top experts for supposedly different tasks.
Precisely. The specialization we thought we were getting, it's just not the main story here.
That's incredible. What about the concentration of work?
Even more striking, they measured the Giannini coefficient, which, tracks inequality.
Right, how the workload is shared.
And it was consistently above 0.88, sometimes even over 0.94. This means a tiny handful of experts is taking on up to 70% of the total computational mass.
And this isn't just a fluke at one layer of the network.
Not at all. This structure, this standing committee, it's there across all layers, shallow, middle, and deep. It's like the model's permanent backbone.
So if the committee is doing most of the work, what kind of work is it? Is it handling the really complex domain-specific stuff?
It's actually the opposite. They found a very clear functional split. The standing committee handles 2 domain-agnostic things.
Okay.
First, the syntactic backbone. High-frequency words like the, E-E-N-E, the glue of the language.
The basic grammar. Makes sense. What's the second thing?
It handles the logical framing. So functional tokens like which, what, suppose, and even question marks. It sets up the reasoning structure.
So it builds the logical and grammatical template. And the other experts.
The peripheral ones.
Yeah.
They only get called in for the really specific low-frequency knowledge. Think chemical symbols, financial jargon, things like that. They fill in the blanks, but the committee draws the outline.
This all feels like it's an emergent property then. Something the model figured out on its own because it works best.
It certainly appears to be an emergent optimization. But here's the tension. Our standard training practices for MoE models directly fight against this. We use what are called load balancing auxiliary losses.
Right, to force the model to use all the experts equally. To enforce fairness.
Exactly. We're trying to spread the work out. But the model wants to centralize it on this highly efficient core.
No, we're literally spending computational budget to prevent the model from doing what it finds to be the most effective thing.
That's the conflict in a nutshell.
Yeah.
We're fighting against its natural optimization behavior. This research really shows that even in these sparse systems, you need a powerful generalist core to hold it all together.
Which brings up a fascinating thought then. Since this centralization is natural for MoEs, what if we just stopped fighting it? What if future architectures were designed to embrace this core periphery structure from the start instead of trying to force a fairness that the model doesn't even want?